Okay, so today we will discuss yung biological modeling of radiation and overview of Monte Carlo methods. This is from Turner. So far we have already discussed uh, uh, 11 chapters of Turner. Yung Monte Carlo methods, we will not discuss it because you already have a working idea of Monte Carlo methods, which is the use of random numbers uh, to approximate uh, real measurement. So yun, so meron na kayong idea ng Monte Carlo, and then dadaanan natin yung chapter 13 ng Turner. So we will not discuss chapter 14 and chapter 15 of Turner anymore. So I think enough na yung 13 chapters ng Turner na overview for you to have a working view ng radioactivity and yung how we assess statistically radioactivity measurements. So our topics for discussion are we will return back to the idea of deterministic and stochastic from our chapter 1 discussion. Diba may discussion tayo ng may deterministic na physics at meron stochastic na physics. The same concept is also present on the effects of radiation. We also have a deterministic effect and a stochastic effect of radiation, especially among living organisms. We will touch on the linear energy transfer model. We will discuss briefly yung single target, single hit model, and then yung multi-target, single hit model. I think dadaanan natin ng mabilisan tong linear quadratic modeling, and then yung ating introduction to Monte Carlo modeling of radiation. So these are overviews. So perhaps when you try working on your special project, you might choose a topic along this line. Okay, let's now discuss deterministic versus stochastic effect. Actually, yung deterministic at stochastic effect, it's a not a true dichotomy, but in reality, yung manifestation ng determinism and stochastic effects ay iba-iba yung pag-express nila. So basically, yung deterministic view, if we want to enter the perspective of someone na who is in the school of thought of determinism, medyo ang tingin niya sa yung titingnan niya ay mga thresholds. So let's say na-reach na ba yung ganitong level? May mga limits, may mga standards. So let's say it's below safety limits, it's below this specific standard. Ibig sabihin, wala pang impact yung radiation kapag below certain limits or standards. Or kung halimbawa mayroong threshold na kapag lumagpas sa level na ito, delikado na. So medyo deterministic yung pag-view ng mga bagay-bagay doon. Kasi you have a certain value na kailangan mo ma-reach or ma-overcome para sabihin na may impact na yung radiation. So yun yung medyo deterministic na view of looking at things. And it's easier to have a deterministic view of things because madaling mag-assess ng safety ng radiation kung meron kang standard or range or meron kang threshold in mind na kailangan hindi mo ma-reach yung value na yon. So yun yung parang deterministic view na may threshold. So let's say meron kang dose. So let's say let this be x. So if less than x, okay pa. Pero pag greater than x, hindi na. So yung standard na ito, pag na-breach, ibig sabihin hindi na safe. So medyo ganun yung deterministic point of view. So we assign thresholds, limits, and standards. Yung stochastic view ng radiation is that there's likelihood of effect no matter how small the radioactivity is. So it's probabilistic. So let's say meron kang dose na less than x. So labi natin it's y. Okay, so yung y, although it's less than the threshold, it still has a likelihood of impacting your cell or your organ or an organism or an individual. So there's likelihood of effect. So no matter how small radioactivity is. So conversely, pwede yung case naman na pwede din naman na super lagpas na siya sa threshold na X. Nandito na siya, let's say this is Z. It's much greater than X. It's a very large amount of radiation. Pero yung large amount of radiation na yon, meron pa ring likelihood na hindi rin mag-take effect. Hindi rin ma-harm yung organism. Although, yung likelihood is very small na walang damage na sa organism. So, yan yung basically stochastic view and deterministic view ng radiation. Okay? Clear? So, may threshold, limit, standard sa deterministic view. Sa stochastic view, likelihood, probabilistic. Okay, so with regards to these two views of radiation, two philosophies with regards to radiation, yung stochastic and deterministic view, we have this principle of ALARA. So especially dahil meron tayong stochastic view, let's say meron kang imaging na ginagawa. So diagnostic siya. So you want to know kung merong cancer yung isang patient. So let's say you have your patient here, you have your patient here. And then you have your incoming radiation beam to radiation to image a certain part of your patient. So you deliberately bombard yung patient mo ng radiation. So yung principle of ALARA is that you should bombard your patient with enough radiation, just enough radiation to do your purpose, which is to image kung meron ngang sakit si patient. So dapat yung radiation mo as low as reasonably achievable. So ang tawag doon is principle of ALARA. Kasi nga, no matter how small your radiation, there's a likelihood that it would have an effect later on. So yung stochastic view na yan give rise to this principle na kung mag-i-image ka man ng patient, you want it to be as low as reasonably achievable. Because kung halimbawa, nagkamali ka ng pag-image sa patient, tapos x-ray mo ulit ng x-ray, x-ray. So yung exposure ng patient mo, cumulatively doon sa x-ray na unnecessary dahil nagkakamali ng pag-x-ray kay patient, yung continuous na pag-expose dun sa patient sa radiation could result to a small risk of having adverse effects later on. Okay, let's now briefly discuss the linear energy transfer model. So basically, your linear energy transfer model has this notion that there's an amount of energy transferred in a track of a radioactive material. So, halimbawa, may naglalakbay kang radioactive material, in the process of the radioactive material moving or yung radiation mo na gumagalaw, it leaves a track of energy. So, yung highlight, ibig sabihin mataas yung nito, linear energy transfer, associated yan with your alpha particles and neutrons. So they transfer a lot of energy at short distances. And then yung low linear energy transfer na particles would include beta and gamma radiation because they travel longer. And as they travel longer, the transfer of energy is not as much in comparison to your alpha and neutrons. So low let yung beta and gamma, high let yung alpha and neutrons. This is from Turner. So let us briefly discuss yung survival probability ng ating cells under high let or low let conditions. So take note that your y-axis is the ratio of your survival probability. So S naught is yung initial population. You can think of that as your initial population. And then yung S is yung fraction of S naught that survived, yung buhay pa. Okay, so look at your scaling system. So this is this is not linearly scaled, so log scale yan. So this is not actually a linear function, not linear, because ang plot natin is naka-log yung scale versus linear dose. So you have a log linear plot. Okay, so take note of the scale. So yung highlight, which is yung high linear energy transfer, pag tinignan nyo, given some dose G, the higher the dose, ibig sabihin yung amount of radiation. So the higher the amount of radiation, mas mabilis bumaba yung survival probability. So bumababa yung survival probability. In comparison to low-let, so low linear energy transfer particles such as your beta and gamma, yung graph is may shoulder ka pa dito. You have this shoulder. Hindi agad diretsong baba. May konting mabagal na pagbaba. So with respect to those, but nonetheless, the survival probability decreases as your dose increase. Okay? So these are your models for your low-let versus high-let in terms of survival probability. Again, as I've mentioned earlier, this is likelihood of survival. So kahit mataas yung dose, let's say nandito na siya, nandun yung dose, meron ka pa ring this percentage of survival because based on this model, may segment pa rin ng population na mag-survive at those levels of dose. Okay, let's now briefly discuss your single target, single hit model. So let's say you have cells here, cells. Okay, so yung single target, single hit, let's say this cell was hit by your radiation. Ibig sabihin, mamamatay si cell pag tinamaan siya. Okay, let's look at some concepts in our single target, single hit model, yung cross-section. Later on, you would have a detailed description of your cross-section as a concept sa higher applied physics courses nyo. But basically, think of your cross-section as proportional to the likelihood of interaction with radiation. So the higher the cross-section, the higher the likelihood of interaction. Okay class? So yun muna. So the higher the cross-section, the higher the likelihood of interaction with radiation. So meron kang absorption cross-section, meron kang scattering cross-section, meron kang Newton capture cross-section, etc. So depende sa interaction, meron kang corresponding cross-section. So ang thing is, pag mas mataas yung value ng cross-section, mas mataas yung likelihood of interaction. So this is your cross-section. Just take it as some constant na kapag mataas yung likelihood of interaction. Okay, let's now discuss fluence. So this is your amount of radiation per given area. So the higher the fluence, the higher the radiation per given area. Maraming disintegrations per given area. Okay, kapag mataas yung fluence. So take note, kapag siksik na siksik yung amount of radiation mo on a given area, you have a very, very high fluence phi. Okay, so ito, yung mu mo, yung number of hits, is proportional to your fluence phi, and then your cross-section sigma. Okay, ito kasi yung sa word na phi, na symbol, kapag word lang. Pero pag naka-equation, ito yung Greek symbol na phi. So, anyway, so your mu, yung number of hits mo, yung possible number of hits is equal to yung fluence. Ano ba yung fluence? Yan yung number of radiation per given area times the likelihood of interaction, which is given by your cross-section. Okay, so yan yung average number of hits, which is given by mu. Okay, assuming a Poisson distribution of counts, so nasa radiation tayo, so Poisson yung distribution, and assume that your dose is proportional to your fluence, where K is some constant of proportionality. So that we now have this. So ano yung probability na may zero hit? Ibig sabihin, mag-survive kasi hindi tinamaan eh. Kasi kapag nagkaroon ng hit na natamaan, patay na yung cell. Pero kapag hindi natamaan, buhay pa. So ano yung probability ng zero hit? So using the Poisson distribution, so you have mu to the 0 e to the minus u over mu over 0 factorial, which is equal to e to the minus u mu, or e to the minus sigma times which is your cross section times your fluence phi. And then we can replace this by this equation, negative d over k. Okay, suppose we have some reference dose k over sigma. So suppose reference dose lang. So with respect to your reference dose DO, kung ano man yung value ng D mo, may factor ka ng pag-decrease ng survival probability. So ang thing din dito sa graph na ito, sa equation na ito, which was shown earlier, is that the higher the dose, yun na lang, yung tingnan ninyo, the higher the dose, the lower is your survival probability, and the likelihood is distributed in such a way na mukha siyang exponentially decaying as your dose. Okay, so this is your single target, single hit model for your cell survival. Okay, let's now consider the multi-target single hit model. So, ganito naman ito. So, suppose you have multiple targets. You have multiple targets. Yan, may mga cells ka. Let's say, and so on. So, let's say these are N cells. So, yan, meron kang N cells. So, sinasabi ng multi-hit target, dapat matamaan mo lahat para mamatay yung cell. So, all should be hit para maging dead yung cell. Okay, so suppose there are N targets and cell death occurs when all the N hits happen. So, yung probability of at least one hit is given by this. So, ito, take note, ito yung probability ng 0 hit. So, 1 minus the probability of 0 hit is given by 1 minus mu. Okay? So, yung probability na meron kang 1 hit is given by this relationship. 1 minus e to the phi times sigma, or 1 minus e to the minus d over k. Ngayon, kung you have N cells na gusto mong matamaan lahat, so you just assuming that yung hitting likelihood ng bawat cells are independently independent from each other. So yung probability na meron kang N hits at least one time measurement is given by this equation. So 1 minus e to the minus d over k raised to the n. Yan yung probability na meron kang N hits at a single time. Okay, so yung probability of survival is yung hindi natamaan. 1 minus this probability. Ulit pala, yung probability ng survival is yung probability na hindi ito mangyari, itong scenario na ito. So that's 1 minus 1 to the 1 minus e to the minus d over k to the n. Recall yung d over k ay ginawa nating d over do for some reference dose do. So yung do natin is d over sigma. Yan. Pinili lang natin yan na do. Well, ano pa rin naman yan? Basta constant lang yan. So we now have our probability of survival given by this relationship, 1 minus e to the minus d over do. So this can be further expanded because when your argument in your exponential is very, very small, pwede ka mag-binomial approximation and then you just collect yung highest order term. So, pwede nyo pang gawin yun further. Okay, let's now discuss ng mabilisan yung linear quadratic modeling. So far, nakita na natin yung survival probability natin is ganito yung form, e to the minus d over do. Itong do na to, pwede natin gawing constant or para mapakita natin na it's equivalent to e to the minus lambda, e to the minus alpha d, where alpha is some constant. Okay, ngayon, in reality, if d is very, very large, very, very high dose, it makes sense to model yung higher order values for your dose. So, pwede ka pa mag-add ng terms na, let's say, minus beta d squared, okay, and then other higher order terms. So your model is now not a simple linear model na negative alpha d lang sa exponential ng probability, but meron ka pang d squared na term. So yan, so yun yung linear quadratic modeling for higher doses. So pwede nyo i-model yan in such a way na ganyan dun sa experimental data na makukuha nyo. So actually, class, may mga experiments on which they model it with real cells, and the linear quadratic model gave a better fit than a simple linear model. Yung Monte Carlo modeling in chapter 12 of Turner class is yung pag-calculate, actually yung isa sa mga ginagawa doon is yung pag-calculate ng pi using random numbers. Yun yung isang exercise na ginagawa doon sa chapter 12 sa Turner. But I think enough na yung discussion natin sa random walk ng pag-generate ng random numbers to approximate yung description ng random walk and to calculate yung variance tsaka yung probability ng position na yung most likely position natin after n steps. So I think you now have a working idea of how generating random numbers can be used to simulate reality. So yan. So I think na-expose na kayo sa rand command sa Excel. In fact, in Excel, you can also generate a normally distributed random number distribution using this command, normin v, yung rand number. You just indicate your mean and then standard deviation, and then drag lang, and then you can generate a normally distributed random number distribution. So yung concept is basically you produce plenty of random numbers, and then you do the calculations iteratively. You do many iterations, and then the more iterations you have, the idea is that you approach closer to the reality. However, ideally gusto natin maraming iteration, but our number of iterations are limited by your computing time and your computational resources. So limited ang memory ng computer nyo to compute for many iterations. And then meron din tayong iba pang gawain sa buhay, so hindi rin pwede na infinite yung computing time. Okay, here is a preview of a Monte Carlo application. So meron ka dito, let's say radiation source, and then with the proper description of how your radiation source propagates emits radiation, magre-release yan ng random particles sa tama yan kung saan. And then pag let's say nandito sa isang part, specific part nung kinreate mo na model, nandito siya. Halimbawa, dito meron kang tally counter dyan. So, may tally counter ka dyan, tapos may tumama dyan. And then, you do the iteration, let's say, 1,000,000 times, 2,000,000 times, and so on. And then, magkakaroon ka ng distribution ng hits at a certain location. So, yung distribution ng hits na yon, makita mo kung saan yung likelihood na may mataas na radiation source, may radiation na tatama sa'yo. So, depende doon sa dose map, makita mo kung saan dapat iiwas. Okay, so ganun din yung naman sa dito sa drawing na ito ay nagdo-drawing ka ng shapes ng organs ng katawan. So you are drawing lungs, heart, etc. And then merong mga factor yan. So later on, when you take higher physics, you would discuss yung mga tissue factor, etc. And then based on those other factors na nasa loob ng software mo or i-input mo manually, meron ka ng model ng human body. So let's say nagawa mo na iyan, yung phantom na iyan sa iyong Monte Carlo software. So mag-introduce ko halimbawa ng let's say isotropic source na let's say ganyan. Let's say this is an X-ray tube. Mag-drawing ka ng X-ray, and then pag nag-on na yung software, magre-release yung X-ray ng beam. Tas yung beam, alam mo yung theoretical distribution, yung input mo sa software. And then from the theoretical distribution, maglalabas ka ng random particles na may known distribution. And then kung ano yung tumama doon sa distribution ng tumama doon sa tao, magkakaroon ka ng idea kung ano yung dose na matatanggap ng specific organ. So, yan yung preview ng application ng Monte Carlo or yung pag-generate ng random numbers to generate random movement of particles na may distribution. So, that's it. So, we have finished yun na yung discussion ng I think 13 chapters of our book, yung kay Turner. Nakadaan tayo ng 13 chapters. And I think magkaroon na kayo ng enough working background to apply yung basic statistics, and then yung statistical view ng pag-assess ng radioactivity. So thank you very much.